So today there are two topics which I wish to cover. So let me see if that works out. So first is this tidal heating and then the environmental effect. So I think what I will do, I will first do the environmental effect, and then if time permits, I will move over to the tidal heating. But anyway, I mean at the end I will briefly discuss what tidal heating is all about, but we'll see how much can be covered. So I will start from here maybe. So the main topic is so broadly speaking, the environmental effect corresponds to the fact that so far all the black hole solutions or the neutron star or whatever we have studied, the external geometry was vacuum, in the sense there was no matter that was present, and we had T mu nu which is equal to 0. But as you know that we all live in a dark matter environment, because there is a dark matter distribution outside our own sun or even the near the galactic center. Second, most of the black holes have accretion disk which is moving around it and it is accreting the matter. And thirdly, there are always third bodies, or more than one body which is present near the vicinity of a binary. So all of these are going to change the result that you expect from your standard vacuum computation. So broadly speaking, the environmental effects has three different classification. One is due to the dark matter, then two is due to accretion, and lastly this is the third body. I mean, in the last lecture, I think Adam mentioned about the resonances that you see, and that appears due to non-separability of your equation, and that is precisely what a third body does. That even if suppose you are studying an extreme mass ratio in spiral, where the motion of the smaller object you can think of as separable, because the central black hole is assumed to be Kerr. But if you have another object which is present, which is the third body, then the corresponding geodesic equation can no longer be solved, it will not be separable, and as a consequence there will be resonances. So this is the topic which I mean there are quite a few developments on that, but I will not go into that because it is difficult to cover all. Accretion, for example, is another thing which is going to change your physics. I mean, how? So first of all, if you have accretion, your space-time can change. There can be back reaction on the geometry due to accretion. And there are again some recent metrics, as recent as 2024, where people were trying to find out what is the effective metric. So you see, if your metric gets changed from Schwarzschild, then as we had discussed before, all the tests of GR, including the tidal love number, they are going to be different. For example, if you compute perihelion precision, and if it is not a Schwarzschild metric, then you will get a result which is different from that 6 pi m square over L square. Or if it is not Schwarzschild, then bending angle will not have the 4 gm over b kind of a contribution. Similarly, the tidal love number also, which we discussed in the last talk, will not be 0, and that is something that people have again probed as early or as late as August or September 2024. So you can see these are all very active areas of research, and there are many directions which are opening up. So I will focus on the dark matter because that is the side where I mean I have done some work, and probably I have more understanding of the dark matter sector than the others. So the dark matter can affect your physics in two different ways. So one is when you are studying the metric of a black hole which is immersed in a dark matter halo, then you can anticipate that due to the rho, the energy density that the dark matter has, and the pressure that the dark matter might have, it will introduce changes to your metric. Just like accretion also going to modify your Schwarzschild metric, dark matter is also going to modify your Schwarzschild metric, and this modification can lead to various changes in your spectra, like for example the location of the photon sphere, the quasi-normal modes, the tidal love numbers, and so on and so forth. Second is, the other option can be that suppose you have a black hole which is here, like our Sagittarius A star, which is standing at the center of our Milky Way, and there is another particle which is moving around it. This can be the extreme mass ratio setting that Adam is discussing, and in this setting the other particle, which is the smaller one, is moving through a dark matter distribution. Now you know that when a particle moves in vacuum versus when a particle moves through water, for example, it experiences some sort of a frictional force, and in astrophysical context this is known as the dynamical friction. So that means when a particle is moving around, along with the fact that it is emitting gravitational radiation, there would be additional dissipative mechanism due to this dynamical friction, because it is getting hindered in moving forward. There would be attraction from the dark matter particles which are at the back of it, causing a friction like behavior. The other thing that can happen is the accretion, because since the smaller object, if it is a black hole and it is moving through the dark matter distribution, so it will also accrete dark matter, and as a consequence its mass is going to change with time. And in extreme mass ratio in spiral, normally we see the phenomena over a long period of time, like a few years for example, and there is a possibility that this change in mass can be appreciable if the dark matter density is high enough in that particular region. So therefore, these are the two main aspects. One is how the metric changes due to presence of dark matter, and second, how the dark matter's presence is going to affect the gravitational wave phasing through the dynamical friction or accretion and so on and so on. So these are the two things that we are going to discuss. So first is black hole plus dark matter, right? So how do you represent a dark matter? So dark matter is represented with a energy momentum tensor, which is diagonal minus rho 0 pt. So you see, rho is pretty obvious because there is a distribution which is present and it has some energy density rho. Now if you leave them at that point, then they are just going to fall onto the black hole, right? I mean, suppose you have a black hole like this chalk, if I drop from here, it is going to come to my hand. So it will fall towards the black hole. Now to prevent that fall, what you do, you have to give it some angular momentum, right? That is why Earth is not falling into the sun, because Earth has some angular momentum, and as a consequence it is moving around sun rather than just plunging into sun. Similarly here also, if you want this dark matter to produce a distribution around the black hole, for example, the individual dark matter particles have to move around black holes, otherwise they will just fall down. So the motion in the circular direction, as you know, produces a velocity which effectively translates to having a tangential pressure. There is no radial pressure, which is of course an assumption, because technically speaking some of the dark matter will of course come to lower and lower radii and ultimately will go into the black hole, but the assumption is the rate of accretion is extremely small. So you can approximate it for the time scale of interest as just particles which are moving in circles around the black hole, and as a consequence there is no accretion. If there is accretion, there would be a non-zero radial pressure, because accretion means it is moving radially inwards, which will lead to a non-trivial radial pressure. So in all the cases, I mean, at least whatever people do as of now, they approximate the dark matter by a energy momentum tensor with a energy density rho and some tangential pressure Pt. On the other hand, for the black hole, I am not going to discuss the rotating case, because rotating solution for this particular configuration is not known yet. The only configuration that is known is static and spherically symmetric. So therefore, my metric or my G mu nu will also be whatever I had discussed before. It would be minus f of r 1 by g of r square and r square sin square theta. So what I have to solve now, given these two, I have to solve for Einstein's equation, which is G mu nu equal to 8 pi g T mu nu. T mu nu I already know, I have rho and Pt which is there, and for the Einstein tensor I can determine it given the metric which has f and g as the two unknown functions. So all in all, I have four unknown functions to solve for. One is the GTT component, Next is the GRR component, then the energy density of the dark matter as well as the tangential pressure of the dark matter. So, I have 4 unknowns to solve for. But with this you can show that you can get 3 equations. 2 equations are going to come from the GTT and GRR component. That is, you use this equation which is GTT is equal to 8 pi g TTT as well as GRR equal to 8 pi g TR. These are going to give you 2 equations, one for F and another one for G. I will write them down in a moment. Then the other equation comes from the conservation of the energy momentum tensor. As you know that by Bianchi identity, capital G mu nu is covariantly conserved and T mu nu should also be covariantly conserved independently. So, therefore, this gives you 2 equations and grad mu of T mu nu equal to 0 gives you the third equation. So, in total you have 3 equations, but as you know there are 4 unknowns. So, that means in general you cannot solve this system of equation, you have more unknowns than the number of equations. Yes, please.
Why the pressure in this one direction is the same?
Because of spherical symmetry. Because if you do not, yeah, but see, the space time is spherically symmetric, but this object is moving here. So, the idea is they would move like on a spherical distribution. You see my point, it's not like a planar circle, in which case of course it would be axial, but it would be like particles moving like this as well as this. Exactly. So, that is why these two.
You can have also the case in which the format is.
That is true, but in which case I can no longer use this approximation for the metric. I should need the, you know, the GT phi component has to be put there, because then it's not spherically symmetric. Yes. So, I agree. I mean, if you apply it to, for example, spiral galaxies, I should not expect them to be spherically symmetric, but for the purpose of calculation as first order approximation, so to speak, this is what we can do. Yeah. But of course, one should try to generalize it, as I mentioned, in the rotating case where there would be axial symmetry and not spherical symmetry, and see what happens. Right? That answers your question. Yeah. See, the point is, if these are rotating, then the whole system will have some effective angular momentum. So, you need some additional components here to take care of the axial symmetry. I mean, there are 2 components. One would be the angular momentum of the black hole, and if this is also like a disk, then there would be angular momentum coming from the dark matter as well. So, the total angular momentum would be linear combination, but you can switch off with a rotation. Absolutely, sure. Yes, the pressure would be different, and also the metric answers would be different. It is only when you, exactly, when you go very close to the black hole, it would look like Schwarzschild, but outside it will no longer be. Okay. So, as I said, for the moment being, let us go with this approximation, because that's where we can do analytical computation and just to get the flavor what is happening. So, I have 3 equations and I have 4 unknowns. So, the way out is that there are 2 things that you can do. So, after this, one generally parameterize this function g of r as 1 minus 2 m of r over r. See, there is no loss of generality in doing that, because g of r is an arbitrary function of r. I have just translated it to this function m of r, which is also an arbitrary function of r. So, this is perfectly fine. So, that means I have rho, pt, f and m as 4 arbitrary functions. One possibility, which would be the logical one, is to keep rho fixed, how the rho behaves with r, and there are many profiles that is known for dark matter, like there are this Hahn-Quiz type profile, there are the NFW profile, there are Einasto profile, then there are 2 fluid models where at the center you have some sort of a, you know, I mean a superfluid kind of a model, while outside it is NFW. There are many ways in which you can parameterize this density profile rho of r. But the problem is, in most of these cases you cannot get an analytic solution. So, we will assume a very simple choice so that the results can be obtained and you can get a feel for the cancers, because if I just draw plots, I mean they are just plots, I mean How do you understand what is present inside that? So they just do that, but instead of that, what people normally choose, I mean, whether it's they being clever or they are trying to fool us, whatever it is, the point is they actually choose the mass function rather than the density profile rho of r. What they choose is a very intriguing profile. They say that I will have my m of r, the first term would be mass of the black hole, which is mbh, and then I will have a term which is minus mbh r, and then I will have mass of dark matter, and if I am not wrong, there is some r plus a naught. So you see what I am saying is that if you go to r equal to 2 mbh, which is the location of the horizon, then the mass is just given by the mass of the black hole. Correct? On the other hand, if you go to a large distance, then I think I should have here some a naught present, because otherwise it is not dimensionally correct. So if you write it, then you see if you go to large distance, large r, then I will have this term boiling down to 1, and I should have it as r, not as r plus a naught. And at large distance, this r cancels with the r over there. So the total mass becomes mbh plus m dark matter, which is what you expect, because dark matter halo is up to some radius. If you are far away from it, the total mass that you should see is the total mass of the black hole plus the total mass of the dark matter. This functional dependence, this r divided by r plus a naught, is actually governed by what choices of rho you have. If you have different choices of rho, for example, if it is NFW or INASTO, this function r by r plus a naught is going to be different. So it depends on your choice. This factor, which is 1 minus 2 mbh over r, is something that is put by hand, just to ensure that at r equal to 2 mbh you do not have any dark matter profile. It is just given by the mass of the black. The consequence being, that is what the interest comes, is that if you write down g of r, you will see g of r becomes 1 minus 2 mbh over r, and then there would be some function depending on m dark matter and others. The consequence is r equal to 2 mbh is still a null surface, right? And that is what they need. See, what can happen after you add this rho and pt is that the zeros of fr may not coincide with the zeros of gr. Correct? There is no reason. F and g are two independent functions. So why should zeros of fr coincides with zeros of gr? If they do not coincide, you realize there is an issue. This is something I discussed in my first lecture, that if you want to specify that my surface, some r equal to constant surface, is a null surface, what I need is that gr has to be 0. That is necessary for being a null surface. But if I want that surface also to be a killing horizon, then I need my f of r to be 0. So if f and g does not vanish at the same location, that means it is a null surface, but it is not a killing horizon. The consequence being, those spacetimes are normally referred to as wormhole geometries, where the fr and gr do not vanish at the same point, and the null surface and the killing surface, they do not coincide. So we do not want that, we want a black hole spacetime only, and as a consequence, this particular choice ensures that f and g vanish exactly at the same point, which is r equal to 2 mbh. Now, yes, yes.
Well, also singularity inside.
At r equal to 0.
No, not equal to 12. If f and g are different.
Not
So if one goes to 0 and the other one not.
Yeah, no, not always. I mean, there would be, that is the point of wormhole spacetime. You can cook up some spacetime for which even if the zeros do not coincide, there is no singularity at that point.
The determinant of the metric doesn't go from 0 infinity.
Yes, so I will give you one example where it can happen. Suppose you have a metric which is, let me see how do I put it. Yeah, suppose you have a metric which is 1 minus 2 m1 over r dt square plus dr square over 2m2 over r, right? So this metric you can easily see that r equal to 2m2 is where this guy vanishes, while this vanishes at r equal to 2m1. There would be a singularity at r equal to 2m1, but the way people argue is that they say that M2 is greater than M1, and the space time sort of goes up to r equal to 2m2, and then there is a mirror symmetric universe on the other side. So it does not go, yeah, so it is not a horizon, because I mean, for horizon to be there, both should be there. It's just a null surface, and you just have a carbon copy of that universe on the other side. So this, but 2m2 is not in your manifold. So you are just going up to 2m2, and then you are again moving to the other universe, so to speak. This is not the full metric. Yes, yes. So this metric, as I said, this is known as the Damore-Solodukhin wormhole, I mean, which they wrote down in 2008. But there are other variants of this which you can cook up, and that's how the singularity is taken. Okay. So coming back to here, so you know what is your G of R, because you know what is your MBH. And after getting the mass function, since you know what is one of the quantities, you can use this 3 equation to determine what is your PT, what is your F, and what is your rho in terms of G, right. So for example, you have a relation which says that M prime of R is 4 pi R square rho of R. Right, this relation is pretty obvious, because what is the mass function? It is simply integration of 4 pi r square rho r into dr. So therefore, if you know what is your mass function, which is given over there, you can just plug that in and you can get what is your rho. Correct? Right? And what you find is that when your r is large enough, this rho, depending on whatever this function that you have chosen, will either be given by the Hörnquist, which is the case here, or the NFW, or the INASTO. Okay, so that comes from this functional dependence. Right, it makes things clear. And then you can determine your PT, which will be, I think, 2 rho divided by r minus 2mr. Now you know what is your M of r, you know what is your rho, because you have just determined rho in terms of M prime. So you know what is your tangential pressure. Yes. Not rho prime, it is M prime. This is dm over dr. What is the issue there? Yeah, I'm just writing a differential form of it. Mass is volume times density if density is constant. If density is not constant, you have to integrate the rho over the volume, right, to get the mass. That is exactly this relation. Right, and r 4 pi r square dr is your 3D volume element, r square sine theta d theta d phi. Since it is spherically symmetric, sine theta d theta d phi you can integrate to get 4 pi and r square remains. Okay. So then you get your tangential pressure, and you can also get your f, this function, by the other differential equation that you get from GTT, no, from GRR. Okay. So that equation I am not writing, because it's every textbook you will find the relation connecting f and g to this in normal cases. I am just writing the 2 simpler equation which you can get. The last equation, for example, comes from the conservation equation, since it relates rho with PT. The first equation comes from GTT equation, and the third equation, which is for f, comes from GR. So that means you have solved everything. You have solved it in all the unknowns are known, the mass function is known, the rho is known, the PT is known, the f is known, right? And yes, please. Mass function, yes. But I would say that if you ask me that what I would prefer, because this is not something that I have done, is that you should choose your rho first. So you choose your rho to be Hörnquist, whatever you prefer. Then you plug that in into this equation, integrate that and obtain the mass function. If you have obtained the mass function, then you know what is your G of R. After you have obtained rho, you can determine PT, because you know the mass function. So that's how it should go. So they have just kept this particular choice for mass function to ensure that the horizon structure remains unaltered. But I think even if you put here, you see what happens if you put here and integrate, then also you will get something where a constant is going to come. So MBH is anyway going to come there. The point is about this factor. This requires assuming that your density distribution actually vanishes when you go to R equal to 2 MBH, which is not expected. Because if you just take a rho which is a function of r, then it can even go inside the horizon, and in which case you will have contribution from inside the horizon. Now, what is the reason for choosing this kind of a extra fact? Yes.
So I'm not able to understand. So NFW profile.
This is not for NFW. Yeah, Hunquist, for example. Okay, okay, sure.
So that is a halo mass function.
Yes.
So these scales are very different. We're talking about black holes and then halos. We know that many galaxies can be included on a halo, right? So
But each galaxy will have a dark matter halo, which is there. So at the center of the galaxy, you will have a supermassive black hole, which is what we are trying to describe, and which will be surrounded by dark matter halo.
the scales are very different, right? Halo, one halo can contain many galaxies, right?
No, I'm just talking about galactic halos. I mean, not about many galaxies inside a dark matter halo. Okay. Yeah, maybe we can discuss it later, but the argument that here goes is the following, that you have a black hole and then there is dark matter halo around surrounding it, and that dark matter is everywhere. I mean, it is most dominant at large distance because baryon density falls down, but there are dark matter even near the Sagittarius A star, and that is what people are trying to prove. Okay. Now, what you can question is about the choice of rho. I think that is the more relevant question, that by just choosing it NFW, whether that makes sense or not, because whether NFW just comprises of one galaxy or more galaxy, or whether we should take something at the core because of the core cusp issue which is present in dark matter distribution. But those are all can be addressed by choosing an appropriate rho. Like as I said, you can choose rho to be a two fluid model where the central region which will have some different rho of r, and after that you will have a different file, and whether that works or not, that needs to be seen. It's just a simple example, I would say, where things you can see how it works out. Yeah, so FR will have a equation. If you want, I can write it down for you, because where is it? Yeah, so FR will satisfy this equation. So if you want, I will write it down. So it is RF prime by 2F, which is equal to MR by. So this is the equation FR will satisfy. Right? So I have three equations, as you can see. One is this, and this is the other one. So I have three equations, but as I said, I have four unknowns. So I need to supply you something extra. So normally people give equation of state, which is how PT and rho are related. But rather here we are supplying the mass function. So given the mass function, you know what is rho. Given rho and mass function, you know what is PT. And again, given the mass function, you know what is A. Right? Makes sense? Yeah. Okay. How much time do I have? Oh, I'm anyway, after this you can see there are two characteristics scales here, actually three. One is the mass of the black hole, second is the mass of the dark matter, and third is the scale A naught, which corresponds to the size of the halo. I mean, up to which this is going to be very important. And what I was discussing is what the existence of this 1 minus 2mBh over r. So this term comes from a calculation which first Gondolo and Silk did in 1998 for non-relativistic case, and which was later on generalized by Sadegian and Cliff-Wheel in 2013. The calculation that they did is the following: you take a black hole and you assume there is a dark matter distribution which is surrounding it, right? So there is some distribution function which is f, which depends on x and p, for example. Then you know there are this Boltzmann equation. You must have seen this or heard about it in cosmology, where you use this collisionless Boltzmann equation in order to evolve the distribution function of dark matter, neutrino, and all these species that is present. You apply the same over here. You evolve this distribution of dark matter using your Boltzmann equation adiabatically and try to find out what happens at a later time to this distribution. What you find is that this distribution vanishes at r equal to 4m, not at 2m. The result that it vanishes at r equal to 2m is a non-relativistic result that Gondolo and Silk derived, and that is what is being implemented here, such that at r equal to 2m there is no contribution coming from the dark matter, as if the dark matter distribution goes to 0 at r equal to 2m. Here it is done by hand. But as I said, you can do it more rigorously by going through this analysis. If you do non-relativistic analysis, it will vanish at r equal to 2m. If you do a relativistic analysis, it will vanish at r equal to 4m. And 4m, as you know, is a special radius, is the marginally bound orbit's radius. And there would be a spike profile to the dark matter. So that means the dark matter distribution will not actually die down starting from 4m. From 4m it is 0, then there would be a peak and then it will follow some distribution. The fact that there is a peak, this is what is referred to as dark matter spike, and its peak happens at r equal to 6m, where you have the marginally the ISCO, the innermost stable circular orbit. So that is why, I mean, this is sort of a toy model to describe that. But again, as I said, you can do all of this with all rigor possible and you will get some answer. I mean, just to give you an example, if you do this calculation in the relativistic context, why this is difficult is because the mass function, for example, turns out to be a hypergeometric function. And then you can understand, you have to take derivative of hypergeometric function which is rho, and then you have to integrate this, the hypergeometric function, to get the function f, and these are all not very easy things to do. So that is why this gives you a very simple example where most of the features that exist in the dark matter distribution goes through. Yeah, I will take. Yes, 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 exactly. Yeah. A naught is the size of the halo, like it's of the order of kiloparsec or so. Like where within which say half of the mass is concentrated, some characteristic scale. Yes. So if R is much larger than A naught, then your total mass is MBH plus MDM. But if R is very small compared to A naught, then it is effectively MBH and some contribution coming from this MDM over A naught ratio. Yes, yes, yes. Uh-huh. It does not matter what I believe, right? I mean, yeah, so I can believe anything. See, as I said, I mean, this dark matter photon conversion requires you some interaction between dark matter and photon, which of course we are not assuming here. It's just, just matter interacting with gravity. No other interaction is present. But if you have that, it can happen anywhere. Wherever there is dark matter, you should have interaction of dark matter and photon. Exactly, it should be enhanced over there, but the point is you need more photons there. Now the only way to get more photon is if you have an accretion disk in that region, in which case you may have photons. But the problem is most of the photons, which is at r equal to 6m, will probably go into the black hole rather than come out. So therefore, even if you have a conversion, I am not sure how much fraction is going to come out. Right, if I remember correctly, there has been some work, I think at IIT itself, where I am from, where people talk about dark matter photon conversion and some sort of a extra luminosity from the photon sphere. Yeah, okay, so maybe that is what you are referring to. Maybe that can be enhanced if you assume this spike. Yeah, of course. I see. Yeah, I'm not sure. I'm not gone into that direction, but I just know that someone has tried it out, so I just alerted you. But yeah, if you have spike and if you have such interaction between dark matter and photon, you should expect some flash of light or maybe higher intensity coming from 6. Yeah, that is something you can of course pursue. Okay, any other question? Yes. Yeah. Rho and PT. See, massive point particle outside a black hole, you would have to follow Adams' approach, where you have a delta function over the trajectory of the particle. Yeah, that is exactly this. Dark matter only comes in this choice when you introduce this A naught and this MDM. So, I mean, see, suppose this M is very small, maybe then it is baryonic matter. Maybe this A naught is very small, baryonic. But if A naught is large, then it's a dark matter. So, it depends on what are these parameters. Right, so you can assume any values for them, but as of now, as I said, this is true for any fluid which is outside the black hole. Okay, it will not be dark matter. The only reason I am saying it is dark matter because this is not interacting with other T mu nu which may be present, but yeah, that's a separate thing. Okay, so the consequence is the following. So I will write them down one by one, and maybe I will erase this. Okay. First is the QNMs. So you can show that omega. So I am not going for the derivation because you know the WKB which we did. So you can plug that this particular metric. You can compute the effective potential. Say at least for a scalar perturbation, that should not be difficult to do. Gravitational perturbation would be tricky because you cannot just say delta of G mu nu equal to 0. You also have to consider perturbations of rho, and there is no reason to believe that perturbation of radial pressure is going to vanish. Even the background it is 0. Then there would be perturbation of the tangential pressure and it becomes a mess which can be solved, but let us not do it here. But the result for QNM you can do it for scalar case very easily through the WKB approximation. So there what you get this omega for dark matter plus BH divided by omega BH. This is 1 plus there would be some number and MdM over A naught. So this is a result that you can prove out of this particular metric. Now suppose this is, as I said, assuming non-relativistic profile, and if you on the other hand take it to be relativistic, you see that this becomes MdM by A naught to the 3 by 2. So first thing, there is a departure from what is your QNM for Schwarzschild. So if this MdM by A naught is something, so generally typically this is of order 10 to the minus 4 minus 5. So these are very small quantities. So with present generation of detectors, gravitational wave detectors, there is no hope of seeing them. But there can be future generation of gravitational wave detectors which will enhance the signal to noise ratio in the QNM. There can also be a possibility where you see some of the inspiral in another detector, like for example Desigo or some LISA or something, and you see the merger, say for example in LIGO or Desigo. In which case, since those detectors will have more sensitivity, they can actually measure, assuming everything is GR, because you see I am using Einstein's equation. So assuming numerical relativity, you can predict what is going to be final mass and spin to an extremely good accuracy. And if you can measure mass and spin to a very good accuracy, you can actually probe things up to order 10 to the minus 4. So that means even though it might seem very small number and may not be probable today, but within 10 or 20 years, it seems like you can actually see deviations of QNM which are of this order, and you should be able to see what is M over A naught. Yes, please.
So omega pH was complex.
Yes.
And so you are saying that the complex structure is the same.
Yeah. So real and imaginary part will both have the same scaling. The real part. Correct. Yes. So both the real.
This is due to a very specific structure.
This is due to.
Form of ANOVA.
No. So this number in front will depend on what you choose here. Like if it is Harnquist, maybe this number would be 1.1. If you choose NFW, this number could be 2.9. But the scaling does not change.
But the complex structure is universal.
Yes. So these numbers of course depends on which profile you choose, but the scaling is sort of universal. Yeah, as I mentioned, like if you considering this, evolution of this distribution function, you can do this evolution assuming non-relativistic physics, like there is no root minus g in the integration and so on. And in the relativistic case, you include root minus g and everything properly and do the evolution. So in the non-relativistic case, which is here, where your density vanishes at r equal to 2m, that is non-relativistic. So there you get m over a naught. If you do the relativistic case where your density vanishes at r equal to 4m, not at r equal to 2m, then you get a different scaling, which is 3 by 2. That is because the metric is very different and that leads to a different scaling. So that means that you can not only check whether it is a dark matter which is present near a black hole, you can also check what is the profile. Is it relativistic, which means it vanishes at 4m, or is it non-relativistic, which vanishes at 2m, from just the scaling of this particular ratio mdm over m. Yes.
So, in normal case, it was the real part was the velocity, photon velocity.
Correct.
So, in this case, would it be the dark matter velocity?
No, in this case also it would be the photon sphere's velocity, because the metric is different. So the photon sphere is no longer at r equal to 3m. Photon sphere would be at a different location, and if you compute things at a different location, you will get this scale. Right? It will still, in WKB, it will always be photon sphere's velocity. But photon sphere, how do you determine? You determine from the GTT component of the metric. But that is going to be different. Exactly. So therefore, your photon sphere location would be different. Your potential will also be different because your metric is different. And as a consequence, this omega pH and lambda pH, the angular velocity and the Lyapunov exponent, they are also be different. And they will definitely depend on this ratio m over n. Yes.
What you just said, then ISO radius and all those.
Absolutely. Absolutely.
How can you just if you do the modeling of the dark matter with the spike and all,
Mm-hmm.
then why will it vanish and have a spike and a ISO? So that ISO location.
No, yeah, it will not have ISCO of the modified metric, but it will have an ISCO of the non-modified metric, so to speak, like just for Schwarzschild. So normally all these radius near the horizon are always mentioned in terms of the black hole mass. You see, and the change of the ISCO will also be of this order, m dm over a naught, right? And since m dm over a naught is a small number, so we expect it to be very close to 6m. Okay. As I said, 10 to the minus 4 minus 5. Then you come to tidal love numbers, which also you can compute. Now, for tidal love number for black hole, if it is in vacuum, we saw that it is 0. Schwarzschild black hole was 0. But now these tidal love numbers will turn out to be non-zero because of the presence of a dark matter halo. And as you can anticipate, these numbers would just be proportional to m dm over a naught. Then there is a very interesting feature that happens. I think this is the result that you get, log of r naught over r. So this is the result that you get. Let us not put it r naught, let us put it a naught over r. So first of all, if your m dm is 0, means there is no dark matter halo, you identically get your tidal love number to be 0, which is consistent with what we obtained in our previous lecture, that is the tidal love number of Schwarzschild black hole identically vanishes. Second, it scales with m dm by a naught, so that means if m dm by a naught is small, the tidal love numbers are also small quantity, they are not very large. Secondly, there is this scale capital R which appears over here. Okay, let me do it in a different way maybe. Yeah, so let me put it the actual result. So it is m dm a naught to the 4 by r to the 5. So this is the actual result that you get. I mean, it does not change much, it's just that the MDM being 0 tells you love number is 0. But the main point is, what do you choose about this scale R, which is present over here. And as you can see, this log term is also present, as you have seen in the context of exotic compact object. But this log is not related to the black hole parameters, but rather is related to the scale of your dark matter. Now, the choice of R, as I said, can be three choices. One, mass of black hole. Second, mass of dark matter. And third, the size of the dark matter halo. There are these three choices. You see, if you choose it to be the mass of the black hole, the tidal love number is extremely large because it depends on a naught to the power 4. If you choose this R to be your mass of dark matter, then also this is very large because it is A naught over m dm whole to the power 4, and as we discussed, m dm over A naught is 10 to the minus 4, so its inverse is 10 to the 4, so this number would be of order 10 to the 16. And of course, I mean, we do not expect such large numbers from a perturbation theory point of view. So therefore, the only choice that we advocated, in particular the fact that R should be MDM, was advocated by Vitor in one of his the earlier paper in 2021. But we argued that that should not be the case because that makes love number as large as you want, like 10 to the 16, 10 to the 20. It should rather be the scale A naught which is present, because that seems to be the most natural length scale there. And if you do that, put capital R equal to A naught, first of all the log term goes away, and secondly it becomes m dm over A naught, which is consistent with our QNM, because any correction that you have has to be of order m dm over A naught, and which is what we are getting from here. But as I said, I mean, you are open to choose your R. I mean, if you do not believe me or like my argument, then I mean, you will have a very large love number, and in principle you should have detected it by now because it's extremely large. Yes. No, it can be, because you see, for there is always this ambiguity what should be the radius. For black hole and neutron star it did not matter, because black hole it should be the radius of the horizon, neutron star should be radius of the neutron star. But if you have a problem with more than one length scale, then what should you choose for this R?
Maybe the question is what we observe.
Exactly.
What we observe is what we observe. So that's not
Sure. But the point is we have not observed this. So that is why there is this speculative issue. If you have observed this, then of course there is no speculation which is there. Yeah, sure. So let me answer it. So for example, in neutron star, suppose you add some other length scale, you get a love number which is a very large or very small, but we get something of order 700 which comes from setting this R to be the radius of neutron star. So that means from observation, you know that this has to be the radius of neutron star per se. But here we have not seen this, because the point is this tidal love numbers appears at 5pn. 5pn means it is V by C to the power 10 as a coefficient of that term, and V by C itself is a small number, and as a consequence you will only see it at very late in the inspiral. And most of the waveform models that people use in order to match with the GR result, they always assume that tidal love numbers are 0. So none of the waveform models that people use in LIGO in order to extract parameters have this information of tidal love numbers. So effectively, as of now, we are blind to this tidal love number, but in future when you are trying to probe it, you should add some parameter, some lambda to that 5pn term and check what is its value. If you see that value is extremely large, that will tell you, yeah, the scale here should be the mass of the dark matter. But physical intuition tells us that it should be the radius A naught, and hence it should be MDM over A naught.
So suppose I am an astronomer.
Okay.
I don't know anything about general relativity.
Sure.
So you come to me and you say, please do this experiment.
Yes.
Because I want to know what is the tidal log number, which you don't know what it is, but don't worry, just give me this result.
Correct.
So which result should this astronomer do?
Yeah. So what astronomers should do, they will have a psi, which is the gravitational wave waveform. To that they will add a term which is lambda V by C to the power 10, and by matching this waveform with some additional terms to what you have observed, they will try to provide me what is the value for lambda. That's all that they can give. Now you see that you come to your theory and you see, well, I have seen this merger, so maybe I can estimate what is my A naught and MDM, say for example, and I can just check what is the R that comes out of it.
But in principle, I mean, you could know from your theory what is R. So it seems like it's completely arbitrary, but
Not completely, as I said, you have only 3 length scale in your problem.
in this sense is arbitrary, but
Yes.
I mean, I would imagine that, I mean, this is a physical quantity.
Correct.
So if I do things properly and precisely, then I should know exactly what the R is. I should not guess.
Yeah, but okay, maybe we can discuss, but there is this ambiguity which is present here, this choice of R. It is not present, as I said, for stars or black holes where you have a well defined length scale. But in this case where you have a black hole plus a dark matter, there is this ambiguity which you cannot get rid of possibly. I mean, maybe we'll find out a way to do it in.
If I throw everything in a computer and I do a simulation and I get the gravitational potential and everything else, principle that's it. So I should have the tidal lobe number as well.
Yes, but that I'm not sure if people have done like numericals.
I just said, but in principle.
In principle, yes, yes,
Should not guess anything. So
exactly.
It's a condition. My machinery runs. Give me back.
Yeah, but I will tell you where the problem is going to hit you is because you see what you will get is Qij is lambda Eij. This lambda you will get, but this lambda is a dimension full quantity. Now you want to make it dimensionless, so you have to divide it with some length scale to the power. That is where it is. But that lambda you can get without. Yes, yes. Exactly. Exactly. Oh, thanks. Yeah. So as I was saying that if mass of dark matter vanishes, then this MDM goes to 0 and you get back 0 love number. Otherwise, you have a correction over and over to GR, and which is also something that you can possibly detect in near future. Yes. When did I say that? Okay. See, relation wise, we are solving the same set of equation. They are both coming from the Pater Einstein's equation. Now, Q and M is like solving eigenvalue problem and obtaining the eigenvalue. Tidal love number is like solving the eigenfunction, but not those eigenfunctions. I mean, it's some other metric element you are trying to solve. So, it's you understand my point. This is setting omega equal to 0, while Q and M is obtained by the same set of equations with omega not equal to 0. So, the equations are same, it is just two different limits of that equation, crudely speaking.
And the boundary conditions.
No, for TLN also you assume purely ingoing wave at the horizon. The infinity boundary condition is different because TLN you do not go to infinity. Remember the picture that I drawn, you go only up to the intermediate zone, but for QNM you have to go to infinity. So that, yeah, the asymptotic condition is slightly different, but the inner boundary condition is same. Both should be ingoing or regular in this particular case. Yes. QNM tidal, what do you mean? Can you? Sure. It, yeah, generally not, because this is done for a separate black hole, a single black hole which is present. So, this is not due to a second. Yes, 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 exactly. Yeah. So, QNM is effectively coming from a one body problem, so to speak, but TLNs are more coming from a two body problem.
How do we get the regularity condition in the horizon?
Just saying that the perturbation is not diverging at the horizon. And perturbation and its derivative. See, the point is if you do polar perturbation, then the polar perturbation capital H is going to diverge at horizon. So, you do not have to worry about derivative. If you do it for the axial part, you will find that the axial perturbation is finite at the horizon, but its derivative is not. So, therefore, what you want is perturbation and its derivative to be continuous or well behaved. Because otherwise, I mean, you know, at horizon you will have very large perturbation. Suppose you want to compute what is the curvature due to this perturbation, that will diverge. So, that means that your perturbation theory is no longer applicable. See, the regularity only ensures that your linear perturbation theory is valid. If it is not regular, it does not tell you anything about what happens. It only tells you that your linear theory is not applicable. Maybe if you do a, you know, the second order perturbation theory, maybe things would be finite, but we do not know. Right? Makes sense? Okay. So, in the remaining time, let me do another thing that I sort of said I will do, which is this dynamical friction and other things. and I will try to give you a very brief idea that how gravitational wave phasing and other things are computed. So let us start. So first of all we'll do things in a very Newtonian way just to get the leading order contribution. Okay? We will not go into relativistic domain and with other complications. So first thing, when an object, I mean two objects are moving about their center of mass, then the Newton's equation tells you that you have G m1 m2, and suppose they are moving in circular orbit, is equal to mu m t by v square. Oh, sorry. Where mu is the reduced mass, which is m1 m2 by m1 plus m. Correct? This is the Newton's laws of motion effectively. All of you agree with this? Okay. Then from here, what you get is that your R naught is related to V square, and on the top you will have, I think, mt, where mt is m1. I mean, let us assume G to be 1 just for fun. Okay. Yes. No. Yeah, if it is no. They are both 1. Asymptotically, they are both 1. Not Schwarzschild. Asymptotically, I will not get Schwarzschild solution. Because asymptotically, this G of R will have a, the ADM mass, for example, would be MBH plus MDM. So I will not get Schwarzschild solution because asymptotically they will both be 1. That's all I can say. Does that make sense to you, or? No, you see, the point is when you go to large R, then if you say I want to keep 1 by R terms, for example, if that's what is your motivation, right? Then you will have MBH over R, but there can be some, R with MBH and MDM multiplied coming from there. So it will not exactly be Schwarzschild if you keep 1 by R term, there would be differences. Maybe I can explain it to you later. Let me finish this. So my point is, even asymptotically, if you keep order 1 by R terms, FR and GR would not be same. They would be different. But to get ADM mass, you actually go to infinity and then do the integration. So there it will pick up MBH. Yeah, that is exactly. Mm-hmm. Yeah, but the point is the rho is never really 0 until you go to infinity. So that, yeah. Yes. Exactly. So that is why I am saying there can be some, MBH into MDM kind of a term possibly. But dimension wise, I think it is a little bit trickier than what I am saying. It can be that it reduces to almost Schwarzschild like thing. But yeah, I have not checked it explicitly. But what is sure is that if you go to R infinity, they both goes to 1. So asymptotic flatness is guaranteed. Okay. So I have this relation connecting R naught and the velocity. Now we also have this relation, which is R double dot equal to minus Gm over R square. Right? Any one, I mean some of the R double dot. Right? Now R, suppose it's a circular orbit, then R is something like cosine omega t and things like that because it is moving in circles. I mean R is effectively constant, but R double dot you can think of is related to the frequency, the orbital frequency of the object square times R naught. So that means I will change it to omega orbital square into r naught, which is m over r naught square. So this corresponds to, coming from the double dot, is the orbital frequency square times the radius at which this is moving, and this is just the force. So this connects me r naught with the orbital frequency. So I will have r naught cube to be related to omega orbital to the minus 2. I mean, there would be masses present, but the scaling will go like that. Is that fine? Now, if I combine these two results, then I get one of the most important results that people use in gravitational wave, which says that you see omega orbital, if I write, so omega orbital is r naught to the minus 3 by 2, correct? Omega orbital is r naught, and r naught to the minus 3 by 2 gives me what? V cube. Is that correct? That means velocity and frequency are related as 1/3 of the power. So this result you will encounter at numerous places. So whenever in gravitational wave physics, people will always talk about, well, in LIGO we have seen from 20 hertz to 1 kilohertz, right? These are the statements that are being made. You can easily convert that to a more intuitive feeling to velocity. Lower frequency means lower velocity. That means the objects are far apart, so they have low velocity. Higher frequency means higher velocity. That means objects are closer to each other. That's why they have high velocity. Right? I mean, with frequency, at least I do not have an intuitive feeling for frequency, but I have a very intuitive feeling for velocity. So this relation can help you to build up that whenever someone tells that, okay, gravitational wave has this much frequency, you can in turn compute what should be the relative velocity in order to get that. Just one thing is that this calculation is mostly done for, equal mass binary and things like that, where you have a relative position. For MD also the same thing holds true, but for the small mass object you can get the velocity. But anyway, that is the relative velocity because the other object is nearly at rest. Right? Fine. Okay. So after you have this relation with a frequency with velocity, then you ask, what is the phase? How do I compute phase? Take any wave. I mean, you have done waves and oscillation course in any physics, right? With textbook. So how is the phase of a wave related to its frequency? Tell me. Frequency is d phi dt. Come on, phase is e to the I phi, and then e to the I omega t, that is the omega. So phase is omega into t. So d phi dt is my frequency. So that means I can rewrite this equation saying that d phi dt is v cube. Correct? Fine, everybody happy? That means that my phasing phi is integral dt times v cube. Right? Nothing, I mean, no black magic is happening. It's just Newtonian gravity, nothing more than that. Clear? Now, as you know, I will do some jugglery. I will write it as dv into v cube into 1 by dv dt. See if you agree. Correct? Very good. Now is the catch. So I am writing it as See if you agree. That's fine. I mean, it's d orbital. This goes away, right? Right. This d orbital dt is what is your gravitational wave flux, and d orbital dv is what you will find in textbooks as E prime. So this is the final result that you get, which is dv v cube E prime. So this is the formula that people will use when you look up any research paper to compute the phasing of gravitational wave. So you can derive it pretty easily. There is nothing there. So E prime, remember, corresponds to derivative of orbital energy with respect to velocity, and F corresponds to the gravitational wave flux. I mean the flux that is coming to us from the binary in spiral. Correct? Fine? Not convinced or what? And people are looking that they are not convinced, but this is how it is done. Now, what is this F? Yes. Sure.
So this only is the orbital motion.
Yes.
So but you are trying to connect to the gravitational wave spectrum.
Yeah, but whenever two objects move, there will inevitably be gravitational wave.
Sure. And it's the same frequency. Well, it's the only parameter.
It's actually twice. I mean, the gravitational wave frequency is twice of the orbital frequency, but that, I mean, it's related to orbital frequency. That's all that you can.
Yeah. It's the only number you have.
Exactly. The two come.
Reduced mass, so probably that's units there.
Yeah, so there would be some mass, total mass, which is present over there, which I have just not written because, I mean, there would be some mass scale which you can always figure out later on. But this result is something which is dimensionally also you can check. I mean, there would be some mt and the distance between the two binary in front, but the integration is effectively this. Right? Now, what you do next is to calculate this. So, determining dE orbital dV is a very simple thing. So, what is the orbital energy? Tell me. Newtonian gravity. What is the orbital energy? R plus half. No, you know what is V in terms of R. Yes, so it would be G m1 m2 by 2 into R naught, say. Right? This is the orbital energy. Now you know what is R naught in terms of V. Correct? So I will write this as there would be masses. I have to be a bit careful because I will need this mass by 2, and R naught is some mt divided by V square, so it would be V square by mt. Correct? Everybody? Now when I am computing dE orbital dt, sorry dV, then I will have a term which is G m1 m2 by, yeah, sure, because I am working with G equal to 1 unit. Sure. So, yeah. So I will have 2V. Yeah, but let us keep G equal to 1 throughout. Let us get rid of it. Makes life simple. I mean, our life simple, observer's life difficult. Anyway, so I have 2 into velocity here. But you notice one thing, that this assumes that these masses do not change with time. Now, if you have these two particles which are moving through this dark matter halo, then as I said, they are going to accrete matter, and as a consequence, their masses will not be constant, they will also grow with time. So, I will have additional contribution coming from, say for example, m1 dot m2 plus m1 m2 dot by 2 mt. There would also be a contribution coming from this mt over here, but okay, let me add it anyway. So I will have minus m1 m2 mt dot by 2 mt square into v square. And then I have taken derivative with respect to t. So, I should multiply this with dt dv. Correct? Chain rule of differentiation. And I know what is dt dv. How do I know? From here, and I know what is my velocity in terms of r naught and so on and so forth. So, and also from here, because I have a d phi dt present over there. So, there would be ways to eliminate this dt dv in terms of d orbital, and okay, let us not get into d orbital, let us keep it as it is for the moment being, we will come back to that later. But overall, you will have a term which depends on v, and you will have terms which depends on time derivative of your mass. And this dm dt which is present will depend on what is the dark matter density that you have. If you have more dark matter density, then the m dot would be larger because it will accrete more and more dark matter. If you have less amount of dark matter, then it will accrete less and less, right? Second is this flux term. So, the flux here will have two components. One is the flux due to gravitational wave, which is our standard 32/5, that expansion, the quadruple formula, because we are doing everything purely Newtonian. And in addition, there would be this F dynamical friction. Because that is also a way in which the system is losing energy. So, that means if you have dark matter which is present, normally I would just have this term coming from d orbital dv, I would have just this f gw coming from the flux law, and I can just plug them back in here. So, I know that this goes with v, and this f gw I know how it changes with v to the power 10 or so. So, I can plug that in, so it becomes v divided by v to the power 10, which gives me v to the minus 9. There is a v cube term over there which makes it v to the power minus 6. Then you integrate over velocity, so it goes as v to the power minus 5. So, you know that if there is nothing, no dark matter, I should have a phasing formula which goes as 1 by v to the power 5. But now you have contribution from dynamical friction, you have contribution from accretion. That means the total phase change that you are going to observe in your gravitational wave will not just be due to this quadrupolar radiation, but also due to the effect from dark matter. Now, one point of caution here is that this is not the only effect that is present. For example, in extreme mass ratio spiral, as Adam was discussing, there would be numerous other effects, like there would be effects coming from self force and so on and so forth, and there can be other post Newtonian contribution to the quadrupolar formula, and they are also going to come here. But the point is, if you think that all those effects you have understood, assuming that, then you get additional phasing contribution from the dynamical friction as well as from the accretion, and they are both related to the density of the dark matter. Right? Is the statement clear? So, that means I am almost running out of time, so I will finish it. So, that means I will have the total phase change to be delta phi GW, which is the standard one, plus there would be a delta phi dynamical friction, plus there would be delta phi accretion. There would be three such terms, and they will all have different velocity dependence, which you can show. For example, frictional forces, as you know, are linear in velocity, right? Similarly, this accretion part, which as I have written, has a v square and dt dv, so they can be combined and they will be of order v square, for example. So, that means there would be a post Newtonian order difference between the two. And when you integrate that term, you will get a different velocity dependence, not 1 over v cube. So, you will get some contribution from this and some contribution from this. Of course, the question is how do I disentangle the two and so on and so forth. But assuming that there is a contribution over and above your dark matter distribution, over and above your GW, and you know that from Lisa, it can constrain a delta phi, which is I think of order 10 to the minus 4 or so. I mean, assuming optimal condition like your SNR is of order 100, you are observing for a time period of 4 years and so on and so forth, you can get a delta phi which is 10 to the minus 4. Now, you know your theoretical contribution coming from this. you know how much you can measure observationally. So combining this, you can tell what is the maximum density of dark matter that you can actually probe using your LISA. And that turns out to be something like 10 to the minus 3 gram per centimeter cube, which is pretty large compared to the standard dark matter density that we have. But yeah, I will just finish and complete. However, if you look at the super radiant clouds, which are often exist, I mean, supposed to exist in our universe, like axionic clouds and so on and so forth, there actually the density can be as large as this. That means with this approach, you cannot distinguish the standard dark matter that you have because it is too low. But if you have black holes with axionic cloud, then you can actually distinguish them using the LISA measurement. And the calculation is not at all difficult. As you can see, it is a very simple Newtonian calculation. Of course, there would be subtleties like how do you compute this, how do you compute that, which requires some perturbation theory, scattering analysis and so on. But modulo all those details, at least the basic physics here is very simple. That is, in the tests of GR, what we did, we computed what is the perihelion precision, what is bending angle, what is tidal love number, and then if you go for theories beyond GR, you get some correction and then you try to constrain them from your observation. Here also, and actually that's how people do constrain things in gravitational wave, is that they compute what is the change in the phase. And how they compute change in the phase? Exactly the same route. You see there would be changes maybe in the orbital energy, maybe there would be changes in the flux, and they are going to add contributions to your original or actual contribution. It just comes from gravitational wave. And you know what is your limit, the limiting delta phi that you can measure. So by combining the two, you can put constraints on the observables that you have, like the density of dark matter or some other observable which you may have here, like the tidal love number, for example, because that also will going to change your phasing by some amount. So this is how the general strategy goes, and you will be able to do physics with it. So I will come to your question. Sure, sure.
This dark matter contribution comes from starting from assuming that there's a density profile, right?
Yeah.
Now, is it always true that the contribution of dark matter will come at Newtonian? I mean, I assume intuitively that the
Newtonian means it will appear at higher post-Newtonian order. It will not appear at Newtonian order.
Yeah, so then that's the exact point, right? So GW, there is a Newtonian contribution and post-Newtonian. It has a post-Newtonian.
Correct.
So I expect dark matter contribution to come at high post-Newtonian.
Exactly, absolutely. So this GW which is here, just for the sake of it, I have done the Newtonian calculation, but it should have higher Pn terms. For example, this dynamical friction appears at 2 Pn and the accretion, if I am correct, appears at 3.5 Pn. So that means they appear at higher Pn order, but if you know what is a 2 Pn contribution, then you can say if there is an excess, that must be due to dynamical friction, and hence there should be a dark matter. Right? So yeah, you cannot do it with simple quadruple formula. You have to include 2 Pn term if you want to give a result. Okay. Yes. V0. Why? Limits of integration? No. See, okay. So I have not discussed this. So you have a massive black hole. Now, if you move circling, you cannot do that. You have to come to lower and lower radii because you are emitting gravitational wave. Even in Newtonian, I mean, relativistic physics, let us talk about. Okay. So gravitational wave would anyway be emitted. For example, Earth and Sun system, that also emits gravitational wave. It's just that the amplitude is very small, so that the radius change of Earth is almost insignificant. But in extreme mass ratio in spiral, when they come closer, I mean, you cannot detect them if they are too far apart. If they are, say, at, for example, 50 m or 40 m, there would be significant amount of loss of radiation. Now, if there is loss of radiation by energy conservation, who should compensate it? This is compensated by the gravitational binding energy, which means the particle should go to smaller and smaller radii. So it's like a spiraling trajectory. So it starts with a radius, then it goes in, and then ultimately it goes near r equal to 6m and then goes inside, after which there are no circular orbits. But the point is, on one circular orbit it spends an enormous amount of time. So that is why it is a very good approximation to treat them as circular orbits. But they are not really circular. I mean, they have to come to lower and lower radius because they are emitting gravitational waves.
So in that formula, what
You should put your initial velocity. Suppose, for example, it enters your frequency band with a velocity, say, which is 0.1 c. Then you should start from 0.1 c up to where your ISCO is there, because after ISCO it is not in spiral. So this formulation does not work, and you know what is ISCO frequency because you know what is your radius of ISCO. So you can determine what is your orbital frequency or what is your velocity. So you put the velocity as ISCO as one limit, and you put your the observational window at the lower limit. This is the lowest velocity that you can detect. Correct? That gives you the total phase change.
what was the epsilon prime?
That is dE over dV there. It's called nothing. I mean, how the orbital energy changes with velocity. This is called the flux, as you know, the rate of change of energy.
One final question. For the relativistic profile of dark matter, it falls up at 4m.
It maximizes at 4m and goes to 0, sorry, 6m and goes to 0 at 4m.
So
Yes.
in that case, the roots of G of r and f of r will not coincide.
They will coincide because they will be at 2m where there is no dark matter. See, from 2m to 4m it is Schwarzschild. Only when you go, so it's like saying, suppose I am here, there is no student in this region, right? So I will only encounter if I am crossing this line. So this is like my 2m. Outside of it, Schwarzschild. Only if I cross this 4m, I am going to encounter all of you, and that's when my speed is going to be less because you will be asking questions and so on and so forth. Yes. Yeah, as I said, like these things you can calculate analytically. So this is again done using perturbation theory, which I am again not going into. So you get some expression which depends on rho 0 and the area of the horizon, because you can see this is an effective cross section you can think of. So if you have a ball which is passing through a matter, then it should be related to the density and the area that it encounters. So it depends on the rho, for example, and you argue that the minimum delta rho that I can see is 10 to the minus 4. That means I should get a minimum rho naught which I can observe. So just equating these two, you will get this bound. Right? Makes sense? Okay. So let me finish and summarize because the food is waiting. So the point is, here what we have done, we have seen how dark matter is going to affect our gravitational wave observable. In both ways, like if I can modify the geometry, then it can affect the QNM as well as the tidal love number. And if I think of astrophysically, then there would be dynamical friction as well as accretion, and they are going to change the phasing of the gravitational wave. So ultimately, in all gravitational wave tests, I mean, as far as I know, it boils down to calculating the phasing, because the phasing gives you the maximum mismatch between two signals, and that is what is going to give you constraint on any parameters that you are interested in. So at the end of the day, you have to calculate what is the change in the phase. Of course, QNM is slightly different. This only applies to the in-spiral. For QNM, you really know what are the frequencies, so you can just add the QNMs and have this exponentially damped sinusoid, which you can again match and get what is going to be the constraint. The only thing that I did not get time is tidal heating, but let us not get into that because we are already too late. If you are interested, we can discuss it over lunch. So I will stop here for questions, and thanks for listening to this boring 5-section lectures.